Hello everybody. We are on our second set of YouTube lectures. Hopefully I've ironed out the sound thing. I've been checking it like mad. It seems like it's working correctly, but I'll give it a go this time. Okay, velocity and position by integration. Well, we've worked forward and we've said that velocity is the derivative of position with respect to time. And we've said that acceleration is the derivative of velocity with respect to time. Now that makes acceleration the second derivative of position with respect to time. And that makes sense. That we know that velocity is the change in position over change in time, so we're golden here. We know that acceleration is a change in velocity over change in time. We're good there. And this seems like a pretty natural consequence to come from those things. Okay. Well, we're going to work the opposite direction now. We're going to actually start with acceleration. In the cases we've dealt with, whether it was gravity or other problems, we've said that acceleration is constant for the kinematics equations that you remember using last year. And those are good ones, don't get me wrong. Unfortunately, acceleration isn't always constant. So because of that, we have to actually, if we can find an expression that represents the acceleration, in other words, we're going to represent the acceleration of an object, we can work backwards and we can use integration to determine velocity and position. And that makes sense. If you can go one way, you can move forward by differentiating. You can move backward by integrating and repeat exactly the same process. In fact, all those constant acceleration equations, remember, are a result of, if we say A is constant, and we integrate that with respect to time, we would end up with V equals, if we integrate A with respect to time, we call that velocity. Well, this doesn't have, the acceleration doesn't have a t component, so when we integrate it, it's going to be A sub t plus c. Remember, this is an indefinite integral, so it's going to have some constant here. And this constant is going to represent the velocity at time equals 0. So then you get V equals AT plus V0. Well, we've done that before. And since position is the time derivative of velocity, that means that, that velocity is a time integral, or, wow, I'm having trouble here. If velocity is the differential with respect to time of position, then the opposite stands to reason that we're going to have whatever the velocity is, the integral with respect to time is going to give us the position. We're going to go backwards. We're going to basically take the area under the curve of the velocity versus time graph. And that area is going to give us the displacement. Now you'll notice that it tells us how far we move, but it doesn't tell us the initial position. That's what we'll need the constant for. So in this case, let's say again we go back to this equation here and we put that in. So we have x equals AT plus V0 dt. Well, that's two terms, so we're going to actually integrate each one. Well, this is t, so we have to up it a power, so it'll be t squared over 2 times times a plus VO. Well, that doesn't have a t term, so if we're going to integrate, it's going to get 1. And it's going to get a constant. And if you look, we can basically, this is going to be the position at x equals 0. This is actually just the displacement. And we can write it in the old standard way that we write these things. 1/2 at squared plus VOT plus x0 equals x. And that one, again, that's one of the equations that we have listed. Now you might say, well, so what? We already had those. But these two tools, x equals the integral of v with respect to time, and velocity is the integral of acceleration with respect to time, mean that even if this is not constant, we can still figure out an expression. We can still figure out velocity and time, or velocity and position, sorry, equations. And you can see why that's important if you remember EFMA. I mean, this thing here is going to be, if you know the force divided by the mass, and you can chart it as a function of time, then you can, say if it's a jet engine or a railroad car or something like that, you can use any expression you can come up with that's mathematical to go ahead and find what the velocity and position are going to be if you can measure the forces on it. So let's do a quick example. This is going to be a pretty short video. Let's say that we have that the acceleration equals, we chart it out, we do one of those those curve fits, and we get that it's negative 8t squared plus 2t. And I would like an expression for velocity and an expression for position. But I'm going to tell you that the initial velocity is at rest and the initial position is 4.0 meters. Okay. Well, first, these coefficients, what are they really? I mean, they don't have any units listed with them. And a lot of times in your book, they will give them. So they have to have units, just in case we're thinking about it this way. Basically, whatever this is times second squared is to give me meters per second squared. So it has to have meters, but it has to be seconds to the fourth. Because when I multiply it times t squared, I need to be able to get meters per second squared. This unit is going to be meters per second cubed, because only one time is going to be divided away. So just in case you're curious. But let's go ahead and figure out what the velocity is. It's the integral of a with respect to time. So that's going to be minus 8t squared plus 2t, parentheses, dt. I only do that because this operator applies to both of them. So we're going to raise the power of that guy, minus 8t cubed over 3 plus 2. This is going to go up the power, so it's t squared over 2 plus c. Okay, now we can kind of simplify this a little. Minus 8/3 t cubed plus t squared plus some constant. Now in this case, they tell you that the initial velocity is 0. So if I put in 0 here and 0 there, I'll just get 0 for this. So really, it's just going to be negative 8/3 t cubed plus t squared, which is great, no problem. Then we'll do the position as well. We know that's the integral of velocity with respect to time. So that's going to be the integral of our new expression here, minus 8/3 t cubed plus t squared dt. Again, nothing horrible. We're just going to end up increasing the power on this guy and this guy. And we'll have a constant 2 because we're taking the indefinite integral. So x is going to be, nope, I'm going to take this away real quick. Okay. And we're going to take the integral of that. It's going to be t to the 4th over 4 times negative 8/3 plus t cubed over 3 plus c, which is going to be x0. Well, these kind of go away nicely. So now I've got negative 2/3 t to the 4th plus t cubed over 3 plus whatever the initial position is, which they gave us back here as 4. So we can just say it's plus 4. Good. Now I want to point out that we said the units for our constant here were meters per second to the 4th. Well, if you look, those units carry through nicely, because if I take that times time to the 4th power, I'm just going to get meters, which is what I want. It's position, after all. And same thing over here. If I look before, I got meters per second cubed as my unit, and that's going to multiply times t cubed, leave me with just meters, just the way I want. And I think that's it. The end. Woo! Party!